question of how the universe began is something each of us has wondered at some point, but what about how the universe will end? What will happen to the stars, the planets and the galaxies? What about the supermassive black holes and spinning neutron stars? One person who's been contemplating this quite a lot recently is astrophysicist Dr Katie Mack, whose new book, The End of Everything, tackles that very question. We got the chance to speak to Katie to find out the latest theories in the subject and what it means to contemplate the end of the universe.
So my name's Katie Mack. I am a theoretical astrophysicist or cosmologist. I study the universe from beginning to end and various aspects of the more mysterious things in it, dark matter and black holes and the beginning of the universe and how galaxies are made and things like that. I'm based at North Carolina State University.
I think probably astrophysics is one of those things that a lot of people find it quite difficult to comprehend, but also just kind of maybe find it quite difficult to comprehend what astrophysicists do. So what do you actually do on a daily basis? Are you based in an office all day or in a lab, or what's the daily life of an astrophysicist like?
Well, it varies depending on what kind of astrophysics you do. Because I do theory work, I don't go to telescopes, I don't work in a lab. I sit at a desk in front of my computer and I write down equations and I write code and I talk to people and read papers and try and come up with fun new ideas. So it's hard to show anybody what I do because I don't have anything tangible to display, and I don't have I don't have beautiful pictures downloaded from space or anything like that. It's really more about thinking about new ideas of how the universe works and trying to figure out ways to test those ideas by thinking about what new telescopes we'll see in the future or what new experiments we'll see in their data, and making connections between theories of fundamentally how the cosmos is put together, how the universe works, and what we'll actually be able to measure.
Do you pretty much have free rein as to what you work on, or are there certain things you have to study?
Well, I have my specialties, so I have work that I do that I have experience and background in. And generally speaking, when you get a grant or a position, you write a proposal about what you're actually going to do and what topics you're going to study and what the interesting questions are, and then you're expected to work on those questions. But one of the nice things about the field I'm in is that I do get to be very creative, and I do have a lot of freedom in terms of what I actually spend my time on. So I often choose projects based on, what sounds really fun and interesting, and the basic criteria are, is this a question that can be answered, and would the answer be interesting? And, would we learn something cool about the cosmos? And if the answer so that all those things are yes, then it's a good question to pursue. And because of the position I'm in, because of the area I've worked in, I do have quite a lot of leeway in terms of choosing the specific topic or method that I'm using.
I think a lot of people listening to this will most likely be following you on Twitter, because you do a lot of outreach on Twitter. Do you find it easy?
Yeah.
Communicating science and theoretical physics and astrophysics to non-science people?
It depends on the topic, how easy it is. There are some topics that are very, very hard to get across, and there are some that are just maybe unfamiliar, and I can just talk about them, and people think they're cool. It is a challenge sometimes to be brief and concise and actually get information out. And so that's a challenge I enjoy. I find Twitter to be it's kind of a literary medium, right? Like it's a form of communication that has restrictions like a poem might, a certain kind of poetry, and so you have to kind of squeeze your message into these boundaries in a way that I find kind of a fun challenge. And there's also a lot of freedom to it. You can write big threads, you can link to other information, you can use images and so on. So it's not that restrictive, but it is a nice exercise in brevity and clarity, because you have to be brief by virtue of the medium, and you have to be clear, because if you're not clear, the fact that it's such an interactive medium means that people will reply and ask questions. And so very quickly if you have stated something clearly or not, and you know very quickly what people are getting confused about, what kinds of analogies work for people, what kinds of terms people are unfamiliar with. And so that way it becomes a very useful tool for learning how to better communicate science and learning, what really connects with the public. And so I found it fantastically useful for just getting better at talking to people and getting better at sharing the things I'm excited about.
I guess it's kind of good practice for something like writing a book, because that's really how our paths have crossed. Your new book, The End of Everything, is probably due out around about this time this podcast goes out. What does the title of the book mean, and therefore what is the book about?
Well, the title of the book is The End of Everything, Astrophysically Speaking. So the astrophysically speaking is a parenthetical there. And the parenthetical is meant to specify that, I'm really being quite literal in terms of the end of everything. I'm really talking about everything. Most people don't actually mean everything when they say that, but I really mean everything. It's really about the universe and how the universe itself will end, and what that will look like, what it would be like to be there if it were happening around us, and what the possibilities are, what we're learning about the universe right now that tells us which direction things might go in the future. And so it's a fun and very large topic, and I've really enjoyed exploring these ideas. I think there are a lot of books out there about the beginning of the universe and not a whole lot about the end. And so it seemed like it would be a fun thing to explore, and a very dramatic kind of idea to wade into.
Without giving us too many spoilers, what are the prevailing theories as to how the universe might end?
Well, the most popular theory, or the theory most accepted by physicists right now, is that we will enter into something called the heat death. So the heat death is this sort of slow fade. It's called a heat death. It's actually also sometimes called the big freeze. It's this idea that over time, everything is sort of winding down. The universe right now is expanding, which means that galaxies are getting farther apart from each other, which means that over time there will be fewer interactions between galaxies, and that'll mean that there's less gas brought into galaxies to form new stars. And so over time, the stars that are there will start to fade away and die, and the particles will eventually decay, and black holes will even evaporate. And so in the very, very distant future, you end up with this universe that's very empty, very dark, very cold, with not very much happening in it. And eventually you get to a state called the heat death, where the whole universe is really, the only thing in the universe really is the kind of waste heat of the destruction of everything in it. And that's why it's called the heat death. And so at that point, you've maximized the entropy, the disorder in the universe, and nothing can really happen anymore. That seems to be the most likely scenario. That seems to be the way we're headed based on extrapolating where things are right now. But in the book, I go through 4 other possibilities that have kind of different motivations in terms of reasons we might look at the data and say, oh, maybe it's going to go that way. And they can be a little bit more dramatic. It doesn't end well. None of these are a kind of happily ever after scenario, but they're all kind of interesting in their own way, and can tell us something about how we study the cosmos and what we're learning from it. Is
there one scenario that ends with like a a tear in space time, or like a tear in reality, or something like that? How does that play out?
Yeah, that one's called the Big Rip. So that one's related to the heat death in the sense that it's driven by the same thing. So the heat death is driven by dark energy in the sense that dark energy is something that's making the universe expand faster and faster. It's making galaxies get farther and farther apart from each other more quickly over time. And we don't know what dark energy is. We think it's probably something called a cosmological constant, which is just kind of a property of space, that every little bit of space has its own expansion sort of built into it. But it's possible that dark energy is something else, that it's a dynamical process. And if that's the case, there's a possibility that it could be a certain kind of dark energy called phantom dark energy, where it's not just that every little bit of space has this kind of stretchiness in it. It's something that's building up over time. And so the dark energy would be getting more and more powerful over time. And the way that we think dark energy probably works, if it's a cosmological constant, is that it kind of, it increases the empty space in between things, but it doesn't actually expand things themselves. So galaxies themselves don't get puffier in a cosmological constant universe. But the empty spaces between galaxies would get larger. But if dark energy is this so-called phantom dark energy, then it does stretch things out that are already kind of compact. So it does actually kind of puff out galaxies and pull stars away from their galaxies over time. And if this is what dark energy is, if it does have this so-called phantom nature, then over time, not only would galaxies get farther apart from each other, but they would themselves be stretched out, and you would kind of start unraveling the universe from the outside in terms of the compact objects. You'd be pulling stars away from galaxies, and then planets away from stars, and then planets and stars themselves would be torn apart from the inside, from this internal stretchiness interior to the objects. And then eventually you can calculate, if you know that this is happening, you can calculate that at some moment, atoms and molecules and particles themselves will be ripped apart, and all of space will be kind of torn asunder, and that's called the Big Rip.
None of these scenarios so far is particularly inviting, is it?
No. Like I said, it really doesn't go well for the cosmos in the end.
When I was at school, I mean, this is probably going to show how kind of old I am, but when I was at school, I think it was about 12, in our physics class, we were taught that gravity is going to pull everything back in, and there's going to be a massive crunch, which obviously, since I was taught that, dark energy has been posited as a theory. But is that massive crunch of everything collapsing in on itself still valid in any way, or is it completely poo-pooed?
So the Big Crunch is an idea that was the favored idea in the 1960s or so, and it has been kind of around for a while, this idea that the expansion of the universe will at some point reverse and everything will come crashing back together and into a hot, dense mess like we had at the beginning of our universe. It's not that we know that it's impossible, but because we know that dark energy is dominating the dynamics of the universe now, that it's dark energy is making the universe expand faster and faster, it's harder to see how that expansion would ever stop and turn around. There was a time before we knew about dark energy when all we knew was the universe was expanding. We didn't know for sure if that expansion would keep going forever, or if the gravity of everything in the universe would slow the expansion down and then eventually reverse it. And right now, it definitely doesn't look like the gravity of everything is enough to reverse the expansion. But since we don't know what dark energy is, there is a possibility that dark energy could be something that could change in nature in such a way as to not cause expansion to accelerate, but cause it to turn around in the future. There aren't that many models that do that in the literature, but it's one of the things that, because we don't understand this very, very powerful component of our universe, the dark energy, we can't really say for sure that we know what it's going to do in the future. So that is still a possibility in the sense of we can't completely rule it out. And that would be a dramatic one as well, a big crunch, because in that case, you would have all the galaxies, all these distant galaxies we currently see moving away from us, they would start to move toward us, and you would have more interactions between galaxies. You'd have these big bursts of star formation, and then everything would kind of get more and more compressed. And the way that it would ultimately destroy everything is that not only would the galaxies come together, but all of the radiation in the universe would be compressed into a smaller space as well. And when galaxies collide, it's not that dangerous for the stars and planets in them, because there's enough empty space in galaxies that the stars get kind of mixed up in their orbits, but the collisions between stars are very rare. But if you're bringing all the radiation in the universe into a smaller space, if you're intensifying and focusing that radiation, then the way that ends up destroying things is that you get to a point where you start cooking the stars from the outside in. You start getting such intense radiation from all of the starlight that's ever shown in the universe suddenly focused into a smaller and smaller space, that it starts to ignite the surfaces of stars. And that's something that was worked out by Martin Rees, the Britain's astronomer royal, in the 1960s or 70s, and it's a very fun idea that the stars would be cooked from the outside in.
If the universe did die, or when the universe does die, is there any chance that it could be revived and be born again, or get a second wind or something like that?
There are models that suggest a cycle between a kind of big crunch and then a new big bang and so on. There aren't that many models that do that, because it's a little bit complicated to figure out the mathematics of why the universe would go through that crunch and come out on the other side. The equations of general relativity, Einstein's equations of gravity, make it very simple to extrapolate, that there was a singularity in the beginning, and if you have a certain balance of expansion and gravity, then there will be a singularity at the end, this kind of arc of expansion and recollapse. That kind of evolution comes very naturally out of general relativity. And we don't think that there was the kind of straightforward evolution in the beginning that suggests either, but the idea of going to a singularity at the end, you can get that out of the equations, but then going through the singularity to something on the other side doesn't come naturally out of that. And so it's not a straightforward thing, but there are ideas of universes that compress and then expand again, driven by kind of other new aspects of physics. And in a few of those, there are possibilities that you can have a kind of compression and then a re-expansion, a new Big Bang, and there are possibilities that a little bit of information might pass through the cycles, and that ends up being a very intriguing idea. And I talk about that in the chapter in my book about bouncing cosmologies, where there could be something that kind of changes cycle to cycle in a really interesting way. But a lot of those ideas are a little bit complicated in terms of how they deal with what gets recycled and how entropy works, because entropy is this sort of disorder in the universe. It's meant to be always increasing over time, and if you have a universe that keeps cycling, the question of what that does to entropy is an interesting one. And do you just increase entropy every cycle, or is there a way that this breaks that rule? So I explore a bit of that in the book as well, and so yeah, there is a possibility that there could be some kind of rebirth. There are a few ideas around that. Unfortunately, we would still be gone, so our observable universe would still be destroyed. But in a few of these scenarios, there is the idea that some little bit of information, probably just like the position of a black hole or something like that, but some little information could survive through to the next cycle.
Say planet Earth existed as it does now, but at the end of the universe, at that one of the scenarios, what would actually happen to human beings? Would you just be sitting in your kitchen having a cup of coffee and then you just disappear, or what would happen?
It depends on the scenario. So, I mean, with the heat death, like just everything would decay. If you managed to stick around through all of that, you would just see the universe getting darker and darker and darker, and eventually, your particles would decay. If you were in a big rip scenario, that would be one of the more dramatic ones, because you would watch the stars at the edge of the galaxy drift away. You would watch the Milky Way kind of fade out in the night sky. You would see the Earth would be drifting away from the sun. It would get darker. You would start floating into empty space, and then very shortly before the very, very end, the Earth itself would be torn apart, would explode in some way, and then your own atoms would be ripped apart. I mean, I was thinking about this when I was writing it, like how would you prolong your life the most in this situation? And what you would want to do is get into a very small space capsule and wait it out, because the problem is that space itself is trying to rip you apart, right? So you want to have as little space close to you as possible. You don't want to be dependent on things that need a lot of space, like a planet. So you get into your little space capsule, and then it's not until very close to the end that space capsule itself gets ripped apart, and then you die. So that one would be quite a scary thing to go through. The big crunch would be quite scary as well, because you would also see that coming. You would see that the galaxies are starting to approach, and you would see that the background light is getting brighter and hotter and higher, higher frequency, more hard radiation, and the universe would just get very, very hot, and that would be quite scary to just be slowly sort of cooked in your own space. Then some of the bouncing scenarios, you might not see those coming, and there's one in which the universe would start to compress a little bit. You'd see galaxies start to come together, and then suddenly you'd be sort of incinerated by this new scalar field, which is a kind of new energy field throughout space. But my favorite scenario is one called vacuum decay. And that one technically could happen at any moment. It could happen right now, right here.
No.
And that one, well, that one's a really fun one, because what happens in vacuum decay is, so you're aware of the Higgs boson, this particle that the Large Hadron Collider discovered in 2012 that has something to do with how particles got mass in the early universe. So the Higgs boson is a particle that's connected to the Higgs field, which is a sort of energy field pervading all of space. And the properties of the Higgs field are connected to how the forces of nature work, the constants of nature, the strength of the electric field of an electron or the mass of a proton, all these kinds of things. So the properties of the Higgs field tell us something about how physics works. And there's this intriguing possibility that particle physicists have discovered somewhat recently, that the properties of the Higgs field might not be fully stable. Like, the Higgs field is an energy field that's kind of sitting at a certain value, a certain energy. And it's possible that that value might change. And if it did, then that would change the laws of nature. It would create, in the place where that changed, it would create a different kind of space, a kind of space that we couldn't live in. And what's been discovered recently is that it seems that there's a possibility that the Higgs field could, in one place in the universe, in some place randomly in the universe, undergo a transition, a quantum tunneling transition. So an unpredictable, could happen at any time kind of transition, where the Higgs field at that one spot would transition to this different value, and it would create this bubble of a different kind of space, what's called a true vacuum. And this true vacuum bubble would expand throughout the universe at the speed of light or thereabouts, and destroy everything in its path. And the amazing thing about this is, not only could it happen at any moment, because it's just this quantum tunneling thing, which is a sort of probabilistic, you can't predict when it's going to happen event. But also you wouldn't see it coming because it's happening at about the speed of light. And since light travels at that speed, you don't have any signal that could get to you before the bubble does. So if this bubble is expanding through space at the speed of light, then it'll hit you before you know it, and you won't even feel it because your nerve impulses don't travel that quickly. And then it'll just wipe out everything, and that'll be it for the universe. And it's a fun idea because it's so dramatic and it's so extreme and final. But whenever I explain this to people, I have to be very careful to say, this isn't actually something you should worry about. So for a number of reasons. I mean, the most obvious reason being there's nothing you could do about it. You wouldn't see it coming. But the slightly more reassuring reason being that we don't know for sure if it can happen, because this is based on an understanding of physics that we know is not complete. But also, although it could happen at any moment, it's extremely unlikely to happen at any moment. When people do the calculations of, how long this tunneling event is likely to take in terms of, sort of what the average decay time of a universe like ours is, you get numbers like 10 to the power of 100 years or even 10 to the power of 500 years. So what that means is that although this event is random, like any sort of quantum event, there's also a timescale associated with it. Just like if you were watching radioactive decay, there'd be a timescale associated with how long it would take all that stuff to decay. You wouldn't know when any particular particle would go, but you know that you expect a half-life of 3 hours or something. And for our universe, that kind of timescale is something closer to 10 to the 100 or more years. So it's probably not going to happen anytime soon, but it could. and that's the thing that I think is the most fun about it.
When you're talking about all these different scenarios, do you think that there's an assumption that physics operates the same way across the universe, and do you think there's a chance that physics doesn't operate the same way across the entirety of the universe?
Yeah. So that comes into ideas of the multiverse. So one of the ways that physicists talk about a multiverse is the idea that there are regions of a larger space, regions of a sort of the universe broadly defined, where you could have different laws of physics, where the constants in nature might be different somewhere else. And that might be because of processes that happen in the beginning of the universe, where you can create different pockets of universe that have different properties, different constants of nature, and different evolutions and so on. So it's very possible that somewhere outside of our observable universe, there are places where physics acts very differently. And our observable universe appears to be pretty uniform, but our observable universe is just defined as the region, the volume around us, where if you think about the sort of the edge of that volume, that's the point where light would have taken the entire age of the universe to get to us from that point. So what we're saying is that, in principle, one could see farther than that, but it would take the light so long to get to us that it hasn't got here yet. So that's how you define an observable universe. And so we have this observable universe around us, and we have a pretty good idea of the properties of space in that volume, but we don't know anything about what's beyond that because we can't see beyond that. And in fact, we never will, because now that the universe is accelerating in its expansion, we're not going to be able to see more objects beyond that point, because they're being carried away from us so quickly by the expansion of the universe. So, what's beyond there, we don't know. And it's very possible that we're in a much, 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 much larger space. And it seems very likely based on what we understand about the beginning of the universe. And that means that, what's in that larger space, it could be anything. And we have reasons to believe that, there really could be very different properties of that larger space, and it's just our own space has a particular setup, but that's because it's a smaller piece of something much bigger.
Do you think that constantly thinking about and asking these questions changes your own view of life and the world and people and human beings? And I was just thinking about that. If you think about the difference between me walking around a city and looking at the buildings and an architect doing that, obviously you're going to think about it in a different way. Do you think being an astrophysicist changes the way you think about life and humanity in the world?
Thinking about the end of the universe constantly for the last couple of years definitely has had an impact on me, and I think that's hopefully understandable. But it does change your perspective in terms of you always have this bigger picture in mind, and you always are aware of the extreme insignificance of the world and humanity in the bigger picture, in the broader context of space and our galaxy. I mean, even our galaxy is insignificant in the bigger picture of the cosmos, and this time that we're living through, where new stars are forming, and we can see huge regions of the universe. That this time is temporary, because in 100 billion years we won't be able to see other galaxies anymore, and stars will be burning out, and you won't be having new stars forming all the time, and these beautiful nebulae with pillars of creation and all of this star birth and supernova remnants and all of those kinds of things. We won't have all those beautiful things in 100 billion years. That's a long time, but it does kind of highlight that this space that we're in, this sort of habitable condition that we're in the cosmos, is temporary. And there's something confronting about that, even though the timescales are so long as to be totally immaterial to a human life. It still does kind of make you think about the broader picture and how we fit into that, and how we should respond to the opportunity we have to understand and appreciate the cosmos we're in. So I don't know. I think that to me it does give me a perspective that makes me kind of appreciate what we have a little bit more, by knowing that it's temporary, and that not all creatures in the cosmos might be so lucky. So I don't know. It's an interesting place to spend your time mentally in this kind of bigger space, bigger picture.
Yeah, that's quite a positive aspect of astrophysics, I suppose, and thinking about the universe. I suppose you were talking there about the effect of thinking about the death of everything over the past few years, but there must be things that you still really appreciate about the cosmos and the universe. What astounds you most about astronomy and astrophysics?
I think that for me, the thing that I find most amazing and most beautiful is how much of the cosmos we can really see and understand, and even though we are these dramatically insignificant beings, we can understand what the universe is made of. We have a very good measurements of the fact that something like 70% of the universe is this invisible dark energy that we don't understand, that's stretching out the universe. We know that about 25% of the universe is dark matter, which is this invisible stuff that holds galaxies together. And we don't know what that is, but we can measure how much of it there is out there, and we can infer its existence. We know quite a lot about the evolution of the cosmos. We know how it's been changing over time, and we can extrapolate into the future. And I think to me, the really most amazing thing is when we study the Big Bang, the way that we can study that is by seeing it directly. So when you look out into the cosmos, you're looking into the past, because light takes time to travel. And so you can see, a galaxy that's a billion light years away. You're seeing the light as it came to you a billion years ago. And when you look at the most distant galaxies, you're seeing galaxies that lived in a cosmos that was less than 1 billion years old. You're looking into this young universe, and we can actually see the light from the Big Bang. We can see directly the light from when the universe was still hot and dense and glowing with heat. And the way we see that is we look so far away that we see a universe that is still on fire. And all around us, every direction we look, if we look far enough away, we see a universe that's still on fire from the heat of creation. And that, I think, is completely amazing. And we can study that light, and we can study the properties of that light from this primordial fire, and we can learn about what the universe is made of by looking at patterns of that light. I mean, it's beautiful and amazing, and it makes me kind of proud of us as humans that we figured that out, and very lucky to be in a cosmos where we can learn that and we can see all that. I think that's really amazing. So that's the thing that astounds me the most.
Well, after talking about the universe freezing and exploding and crunching, I think that's probably that positive note's probably a good place to end the interview. So thanks very much, Katie, for speaking to me.
That's all right. Thanks for having me. It's been a lot of fun.